Hello everyone. So, a drone, a motor, a temperature controller, even a missile system, all of them can be represented using a same control system tools. In this video, we will understand the most important representation used in control system. So, our first topic today is representation in control system. So we will see representation in control system and block diagram representation in this lecture. So let's start. In control system, we don't directly analyze complicated physical system. Instead, we convert them into mathematical or graphical form that are easier to understand and design. So for these designing purposes, we have four type of designing techniques. Number one, which is block diagram representation, signal flow graph representation, RLC network, and differential equation, which is used in state space model. So first, we will see block diagram representation. A block diagram representation consists of a system shown in the terms of block. The block shows the gain and the relationship between the variables. So now we go to the signal flow graph. A signal flow graph is a directed graph in which nodes are represented as variables. So these nodes are variables. So these nodes are variables and directed branches represent the flow of data. So these branches represent the flow of data. Like if there is an RS and CS, so what is the system here? The RS is going to the this node. This is one variable. Then this variable will go with the gain GS to the next variable and then go to CS, and a feedback path of minus HS negative feedback will move to RS. So this is a basic understanding of signal flow graph. Now we will move to RLC network. RLC network is an electrical network which consists of R, L and C. So now we see the relationship between RLC. We will study about these in next topics like state space models. Now we talk about the differential equation. A differential equation, we will put the differential equation like these. And this differential equation will be used in state space model like x1 equals to x1 bar equals to x2, x2 bar equals minus L1 by LC, x1 minus R by L, x2 plus 1 upon LC V in G. So this is only an example to show what is a differential equation, how it is described. So now we move to the important topic of today, block diagram representation. So block diagram representation have some standard topologies which have series, parallel and feedback topology. The series topology have RS gain connected to a G1 gain and G2 gain. RS is the input here and CS is the output. So CS equals G1 into G2 into R1. So this RS is multiplied to G1 and G2 give the CS. So now we take CS by RS, which will give us transfer function. This transfer function equals G1S into G2S. Now this is very basic terms of topologies, parallel topology, which is also known as feed forward topology. There is RS feeded to two networks G1S, G2S. This G1 and G2 is summed here and gives us CS. So there is a summation and will give us CS. So CS equals G1S RS plus G2S RS. We will take RS common here. RS will be taken as common. Here will become G1 plus G2. So the gain, total overall gain becomes G1 plus G2. Here the over total or gain becomes G1 into G2. Add to the next feedback topology. Feedback topology. Feedback from the output is taken to the input. What this feedback does, this feedback remove the disturbances from the plant. This feedback remove the disturbances from the plant and make the system stable. So we have the two type of feedback we had discussed in the previous lectures. So now when we calculate CS by RS, this will give us transfer function, and this transfer function will known as closed loop transfer function. So now feedback topology, which is very important to our syllabus point of view, we see RS is given to CS. This CS with a path goes through the input, and input will have an error signal. This error signal will again go to GS and generate the loop. So there is an open loop transfer function. So what is a open loop transfer function? So open loop transfer function means only this part. If we broke this from here, the RS will go to GS and HS, the transfer function broke. This is known as open loop transfer function. And the gain, if we see from the series topology, if we have G1 and G2 as cascade network, this will become G1, GS and HS in cascade. Open loop transfer function will become LS equals GS into HS. So it is the block in the forward path and the feedback path when loop is opened at the summing junction. So this is clear. Now, what is closed loop transfer function? Closed loop transfer function is nothing but CS by RS ratio. We can also calculate this as BS will go here, BS will equals BS equals, then this will become BS equals this, ES, now CS. So this is the final equation we will get CS, ES, BS. We will put BS here. This will equals to CS into HS. This CS we will take as common. So what will be left here? The overall equation will become CS 1 plus GS HS equals RS into GS. Now we will take CS by RS ratio, which will comes out to be this. Now we will move ahead to the error transfer function. Error transfer functions comes out to be ES by RS equals 1 upon 1 plus GS HS. This is very important transfer function. So if the feedback is unity, means HS equals 1. So open loop transfer function will equals to GS, which is forward path gain. CS by RS equals GS upon 1 plus GS, HS equals to 1. ES by RS equals to 1 plus 1 upon 1 plus GS. So every system has some basic terminologies. Here are also very basic terminologies which we will discuss in whole control system, and these are always the same. The first terminology is gain. Gain is a constant multiplier in. Gain is nothing but the constant multiplier. Zeros is the if we have some transfer function and it is written in some terms of fraction, and this is s minus z1, s minus z2, and s minus p1, s minus p2. In the terms of this, the z1, z2, z3, z4 will give us zeros, and p1, p2, p3, p4 will give us pose. Now we move ahead to forward path gain. What is forward path gain? It is nothing but GS only. It is the path which is forwarded to from RS to CS. So if there are multiple paths forwarded from RS to GS, the gain can be different as well. Like in previous example, the forward path gain from here to here is G1 and forward path gain from here to here is G2. So there can be different forward path and different forward path gains as well. The feedback path gain is only the path which is connected to feedback. It is known as only at what is forward path, only the path, this forward path, and feedback path is only taken as the feedback path. So what is open loop gain? Open loop gain, we will break this from here. When we will break this from here, this will give us GS into HS. Closed loop transfer function, it is derived earlier. CS by RS equals GS upon 1 plus minus GS into HS. We will take plus sign for negative feedback and negative sign for positive feedback. This can be derived very easily when in previous part I have taken here negative feedback. We have error signal RS minus BS. For positive feedback, we will plus it. So the equation will have plus sign here and minus sign here. This will give us GS upon 1 plus minus GS into HS. Error transfer function. This we will discuss in time domain response analysis in very detail. The very important thing here is the definition of characteristic equation. The characteristic equation is the equation of the denominator of the closed loop transfer function. The characteristic equation determine the root of the transfer function. So we should always know that the y characteristic equation is important, is it determines the stability of the transfer function. So if the transfer function has some poles and these poles are all lies on the left half of the S plane, then the system is stable. So this is all about today. Thank you.